Hello, I'm Athanasios Kritikos. I'm a PhD candidate at Rutgers University, and it is a great honor to be at this virtual conference of AICHE. The following work is about a combined CFD and experimental study on the adsorption of biomass-derived molecules in packed bed microreactors. The outline is the following. We're going to start talking about why the research on the hydroxymethylfurfural, the so-called HMF, is essential. Proceed on how the experimental setup works, what equations and parameters were essential in order to model it, and finally, since we're talking about an adsorption process, we tried different isotherms, adsorbents, and we evaluated how potential changes in our setup can affect the adsorption process. Finally, through this work, we ended up to some take-home messages. US currently is a massive producer of dry tons of biomass of about 36.5 million per year. This biomass can be derived from various supplies like forestry, waste, and agricultural resources. A great percentage of this biomass is consisted of cellulose, a biopolymer that can be broken down to glucose. The chemical that we are interested in, HMF, is a product of glucose. Through its production, there are multiple steps and byproducts. Glucose has to isomerize to fructose, and fructose has to dehydrate to HMF. Through this process, there are unwanted byproducts like the humins and a handful of important chemicals like labulinic and formic acid. Through this chain of reaction, the HMF is the one that we are mainly interested in since it has multiple applications from biopolymers, biofuels, in pharmaceuticals, and so on. This can be attributed due to the fact that it has two very active functional groups. For the separation of HMF, we built the following setup at the University of Delaware. The setup is consisted of an oil bath where the column is submerged. The inflow is inserted by an HPLC pump, and on the outflow there is a quenching and a back pressure regulator. Zooming in the column, it is consisted of the adsorbent and the flow is going upward. There are two kinds of adsorbents used, like the polymer-based activated carbon PBSAC and the carbon black pearl BP2000. These two materials have different properties like porosity, particle size, density, and so on, and the details of this are on the right table of the scheme. For the column, we performed a finite element solving method, and for the meshing, the element size is about 0.3 millimeters with about 2.5 million elements. Some initial and boundary conditions are on the table on the left of the main scheme. After describing the solving method, we now can move on the equations and the assumptions for this model. For the fluid dynamics, we have used the Brinkman equation with a porous zone assumption. For the mass transfer equation, we have incorporated both diffusion and dispersion phenomena and the adsorption where it was simulated by trying both Langmuir and Freundlich isotherms. For this model, we hypothesized an equilibrium homogenized porous media where the bulk species are in equilibrium with the adsorbed species. Other assumptions that we have taken into consideration is that the intraparticle diffusion is dominated by surface diffusion. The surface diffusion coefficient is constant. The instantaneous adsorption occurs on active sites, and the adsorbent particles are spherical. The objectives then of this work were to build a 3D model that can predict a continuous flow separation column from batch experimental data, and different isotherm models and adsorbents were tested. The influence of the adsorption isotherm parameters, diffusion and dispersion coefficient on the breakthrough curve was also examined. The competitive adsorption effects of the fructose dehydration of different chemical components was tested, and the effects of operational conditions like the flow rate, inlet concentration, and the length of the column in the process was also evaluated. After all, an overall design optimization for the HMF separation column was performed. Moving on to the isotherms, the modeling of a continuous flow adsorption system requires the isotherm adsorption constants for the mass transfer conservation equation. In order to acquire these parameters, some batch adsorption experiments had to be conducted, and single solute isotherms were fitted for fructose 5-HMF, formic acid, and levulinic acid on both our adsorbents. The most common isotherms are Lagmer and Freundlich. So at the beginning, we tried Lagmer, but the fitting was not satisfying enough. So we also tried the Freundlich model, where finally we got for all the components a lower mean squared error according to the table here. We proceeded then with the Freundlich model. Then moving on to the adsorbents, both adsorbents exhibit important characteristics like specific surface area, high active sites, adsorption capacity, and so on. In order to compare these two materials, as we said, we fitted the Lagmer isotherm. Through this fitting, we could provide an estimation for the static adsorption capacity of the HMF, levulinic acid, formic acid, and fructose for both materials. The PB-SAC shows higher adsorption capacity for 5-HMF than the BP2000, while the opposite trend is observed for fructose, formic acid, and levulinic acid. The outflow from the concentration, the so-called breakthrough curve, is about the same time for the two adsorbents. So that means that both columns get saturated at about the same time. And this underscores the potential of PB-SAC to be used instead of BP2000. And this is the material that we're going to proceed with. Moving on to the sensitivity analysis, then a sensitivity analysis of the HMF adsorption was performed in order to investigate the performance of the model parameters and to determine which of these are the most significant. The sensitivity analysis is executed by varying one parameter while maintaining the rest of the parameters constant. The influence of the Freundlich parameter, the Freundlich parameters, like the Freundlich constant Kf, the adsorption intensity, and concentration reference Cf, on the observed breakthrough curve, breakthrough time was examined. By varying this Freundlich parameter within a 10% change, we observe a significant effect on the breakthrough time, mainly by changing N and Kf parameters. The trend of the simulated breakthrough curves agrees well with the acquired from the experiment data, and the breakthrough time is about 60 minutes. The influence then of the diffusion and dispersion coefficient of the breakthrough curve was also studied. The fixed first law relates the diffusive flux to the gradient of concentration as a function of diffusion and dispersion. The dispersion coefficient then can be written as a function of longitudinal and transfer dispersivity following an isotropic dispersivity model. Both diffusion and dispersion phenomena influence the curvature of the breakthrough curve. The sensitivity analysis, though, revealed that mainly diffusion coefficient and longitudinal dispersivity affect the sharpness of the breakthrough curve, and the transverse dispersivity had no effect. Since the diffusion coefficient is known by the literature and the transfer dispersivity has no effect, the value of the longitudinal dispersivity got fixed, is fixed following the sensitivity for the following sensitivity analysis for every component in order to fit better the mass transfer phenomena of each component in our setup. Then we move on again to the chain of reaction for the production of HMF, where we're going to have a closer look on the dehydration of HMF and the products of the HMF, formic and levulinic acid. According to our model, the dynamic adsorption capacity in our continuous flow is the highest for HMF. So we were able to predict and match the experimental data on the breakthrough curves with the rest of the components on PB-SAC using the Freundlich parameters and the estimated mass transfer phenomena from our sensitivity analysis. We are able to make a fair comparison between the breakthrough curves of the different components. Specifically, the saturation time needed for formic and fructose were between 5 to 15 minutes, while for the levulinic acid was about 30, and double for the HMF was about 60 minutes. Since the HMF is absorbed more than the rest of the components, and since according to publications, HMF can reach more than 80% yield on a fructose dehydration reaction with aprotic solvents and 50% yield for just water solvent, makes PB-SAC a very promising adsorbent for the separation of HMF from the rest of the components. Moving on to the parametrical analysis, an increase in the flow rate, as we can see from the first graph, leads to a decrease in time needed for the column to be fully adsorbed. Since the feed flow rate affects the convective mass transfer, but not the axial dispersion or the surface diffusion, the curvature of the breakthrough curve is not influenced much. Also, the breakthrough curve changes its saturation time with the flow rate, indicates that the mass transfer is the limiting step and not the adsorption rate. Through the right graph, the depiction of the adsorbed HMF on PB sac adsorbent can confirm that on about 60 minutes, the column has reached its maximum capacity and the adsorption process is done. The rest of the components didn't respond the same as HMF, but in all cases, they got saturated in less time when the flow rate was increased. From this parametrical analysis, we can effectively separate HMF from the rest of the components in less time by increasing the flow rate. We also performed an analysis for the effect of the concentration inlet on the breakthrough curve. The saturation time of the column got decreased as we increased the concentration, and since the curvature got influenced too, the dispersion and diffusion fluxes changed. Increasing also the length of the column, we also increased the active site's capacity, and proportionally the adsorption time was increased and the bed adsorption efficiency got higher. To sum up this work, some conclusions that were essential were that the Freundlich model can effectively fit the batch adsorption data and give us reliable predictions for a continuous flow system. The PB-SEC adsorbent can be more efficient for the separation of the components from the BP2000. A deviation or even a wrong estimation of the Freundlich parameter can severely affect the estimation of the continuous flow model. In our case, the modified Freundlich isotherm could successfully fit the experimental data. The diffusion coefficient and the longitudinal dispersivity influence the curvature of the breakthrough curve, while the transfer dispersivity does not. A higher flow rate can decrease the overall separation time of HMF from the rest of the components, and a higher concentration inlet and a longer packed bed column will of course increase and improve the column efficiency, but also the estimated saturation time can be predicted. Finally, I would like to thank my research group for their constant feedback for my work, our collaborators from University of Delaware, Dr. Ira Petritu, Dr. Vlachos, and his student Yung Wei Xiao for providing the experimental data and guidance. Finally, the funding provided from Rapid and Rutgers University were essential for this work to be presented to you here today. I will be glad to answer any questions on my personal email here. And thank you very much for your attention.